Hello everyone, welcome to the last workshop by the CPMSOC this year, and we're going to cover the famous algorithm paradigm, which is divide and conquer. I'm sure that many of you guys have already heard of the term divide and conquer, and many of you have already seen an example, which will be the merge sort. That is a divide and conquer algorithm, and it covered in Comp 2521. But for those who haven't, we're going to go through this step by step in our workshop today. It's a classic example for divide and conquer. So in today's workshop, we'll be covering the intuition of the divide and conquer, the exact definition of divide and conquer, and applying the master theorem to analyze its time complexity, and going through the few examples, including the merge sort and a problem involving knowledge of the stock price, which we'll be seeing later, and I do not wish to reveal too much detail, and one question involving some graph theory, which will be exciting. So let's get started. Divide and conquer. Divide and conquer is a common and powerful problem-solving paradigm. The intuition of divide and conquer is simple. We encounter some complicated cases, and often the time complexity will be greater than O(n) squared if we just use a brute force method. Then we realize we should blame the question side. We can just divide the question into the sub-problem, which have exact same problem, but which contain the reduced problem sides. So we're gonna do that. And we use recursion to handle those sub-problems. And by the power of recursion, you can assume the sub-problem just solved by itself. And the last step of our divide and conquer, which is combine those sub-problems to solve our current problem. And that's how we solve the problem. We'll be seeing the example later. I'm sure you feel abstract, right? But let's look at the merge sort. Merge sort, the problem is that you are given a list of numbers that we want to return a sorted version of that list. So our step one would be trying to attempt to solve the problem in brute force, such as one algorithm I can propose here is that we always pick the greatest number in the list and put it into a new array and repeat the step for n time, also known as insertion sort. And then we come up with O(n) squared algorithm, which at this point we want to use divide and conquer to improve our naive brute force algorithm. So I propose that we will split the array into two halves, and then we will be calling ourselves, which will be using recursion to sort each half. And by the power of recursion, we can assume that both subarray being sorted, which it haven't, but we can assume that. And then we now consider how do we combine two sorted array into one final array that is being sorted. To do so, it's actually very simple. We propose a very simple algorithm. Our basic idea is to choose the smallest element among two sorted array, and then we remove it from sorted array, put it into the final array. And this step only takes constant time because both array being sorted, the smallest element is always at the start, so we only need to inspect two elements at one time. And we just repeat this step until one sorted array is empty, and then we can append the remaining of other sorted array into our final array. The time complexity would be O(n), and it's a linear algorithm, which we can observe this diagram. We initially have an array, then we call recursion on it, and then we receive two halves, which each being sorted. Then at each step, we just choose the smallest element among two arrays that always, and this take over one time, do constant time, and then we repeat that. So in the first time, on the first step, we choose one from the right array, and for the second step, we choose two from the left array. For the third step, we choose the two from the right array, and we just repeat it, and it's very simple. And the last thing is that we want to discuss about base case because we don't want to go into the infinite recursion. And in merge sort, the base case is when the array size is equal to 1. And in that case, it's being already sorted. And we can conclude our merge sort from here. It's a very simple algorithm, and its idea is very intuitive. Then the time complexity would be O(n) log n but we will discuss that in later question. And now let me introduce the divide and conquer, represent the real definition of divide and conquer. Divide and conquer is a paradigm, and where we solve the problem recursively and apply the following step at each level of recursion. We divide the problem into number of subproblems, which have a smaller instance of the current problem. And in merge sort, our problem is to sort the array. And what we do is that we divide it into two halves, and we still want to sort the two halves, which is like two smaller instances of array. And then it's conquer. Conquer is like solve the subproblem recursively. Divide the problem if size is still too big, and it's also known as recursive case. But we solve the problem if the problem size is smaller enough, which we can just solve it in straightforward manner, which is known as base case. In our last example, the base case is where the array size equal to 1, and for the recursive case is for its size greater than 1. And then the last step, which is the important part, which is combine. Combine the solution of subproblem into the solution of original problem. Sometimes we want to solve a problem that is differs from the original problem, and if that happens, then it's counted into the combine step. And we'll see example in short. And those terms are important in later complexity analysis. With those three steps in mind, let us proceed to the next problem, which require a bit of knowledge of stock. Actually don't. So, okay, the problem, best time to buy and sell stock. Some of you might get familiar, and you are given a list of price with stock in next n days, and you are allowed to buy one stock and sell it in a later day. And you want to determine how to get your maximum profit. The question is pretty simple, right? And there's a diagram. We can see the stock change a day, the price corresponding. The price of stock corresponding to date. And we want to buy a stock at lower price and sell it at higher price, aka buy low, sell high. That's our strategy here. And some of you guys must think, hey, can we just buy it at lowest price and sell at highest price? And yep, it's great, but it's not always been possible. What if the lowest price is after the highest price? Then we simply cannot do that, right? So let us propose another solution. It's a great solution. We run a brute force. We try every possible pair, which is we try every pair of date. And how many pairs can we find? It will be and choose two such pairs, and also known as big omega n square. And it's great. It's very intuitive and it's very simple, and we can implement it very easily. And now we ask ourselves, can we improve upon this solution? But sadly, we cannot. Oh, just kidding. Of course we can. We're gonna use divide and conquer for this. So we come up with a naive solution, but we aren't happy about its complexity. So we want to think of a divide and conquer algorithm. In order to design a divide and conquer algorithm for this question, we want to look at the data in a slightly different way, a slightly different perspective. Instead of looking for a two date that results in maximum difference, we want to looking at the direct change of the price instead of direct price. A direct change of price is the change between the price from last day to today. For example, from day 0 to day 1, the net change is 13, which we refer to the direct change of price. And then, instead of looking at a pair of dates that give us a maximum profit, we wish to find a sequence of dates which the net change of those dates can be maximized. Because the net change is basically the change will be our profit, and then we want this profit to be maximized. So we look at the net change of those dates, and I include a new set of data which indicate the change. And what we really want is to find a subarray so that its sum is maximized. Then we have a new problem. which is we call it maximize the subarray. And the question is follow. We are given a list of change of price, and the ICE index indicates the stock price change from I state to I+1 states, and we want to find the subarray that maximizes the sum. Before our divide and conquer, just one thing that is worth noting is that the array might contain negative number. It's very intuitive because it's net change and the price goes up, goes down, so of course the change can be negative. And why it's important is because suppose that price is always positive, then we can simply return the sum of whole array. But obviously we cannot do that in this situation. So let's continue. Let's try to use divide and conquer for this problem. Then the first step, of course, is to split the array into two halves, and by the power of recursion, we now have the maximum subarray content on both halves. Then we want to make some key observation. So we make proposition here. The maximum subarray is either entirely contain the first half or entirely contain the second half. Or it must crossing the midpoint, which is sort of like intersect with both halves. And then, as we discussed above, we can notice that the first two cases, which are entirely in first half and entirely in second half, can be solved by our friend recursion. And all it's being left is for us to finding the maximum subarray that crosses the midpoint. And also, like another thing we want to notice here is that finding the maximum subarray cross middle point is not a small instance of the same problem because it adds an additional constraint. So it's very important. And by this like additional constraint, we can actually come up with a clever solution to solve it in a linear term. We propose a solution here. We observe that any subarray that cross the midpoint is made of two subarray. One intersect with left half, and also it cross mid, and another entirely in the right half, which also cross mid. Also, this diagram is only indicates that what I'm saying is like the subarray is either entirely in the left half or entirely in the right half, or it might cross the midpoint. And this next diagram indicates what we just said. So only considering about the subarray that are crossing the midpoint, then it can be composed of two components. One is in the left half and cross the midpoint, and one is on the right half, also cross midpoint. And what we can do, like then it's actually very intuitive right now. We can just do it in linear time using sort of brute force method. So what I'm proposing here is that what we can do is like examine the left half, like output for a subarray that cross the midpoint in the left half. Oh, wait, let's go back to the diagram. Let me just show you. So what you can see here, if it one cross midpoint, then there's only like linear possibilities, if that's a word. What we can do in this algorithm here is that we just examine all those possibilities and then we select the greatest one. And similarly, we can do the same thing for the right half. Then what we return will be the sum of both two. Then we have our algorithm. Look at the slide. Each function returns the maximum subarray corresponding from the low to high, and then we use recursion to get the left max and give the right max corresponding to the maximum subarray in two halves. And then we run the cross min max, which is O(n) complexity, and then we return the greatest among those three. By running cross min max plus our discussion of our subarray, so that the subarray is either entirely contained in the first half or entirely contained in the second half, or it calls a midpoint. We can confidently say here, since we are returning the greatest subarray among all three possible outcomes, then it must be the maximum subarray for our current array. So we can conclude this problem. Next, we're going to talk about the master theorem. What is master theorem? Master theorem is like a cookbook method for solving recurrence problem. By applying master theorem, we have to memorize the three cases, and then we plug in the number and we derive our time complexity. And don't be scared by the math equation. Let's talk about each individually. So A and B are constant. A is indicate like how many subproblem, and B is the size of new subproblem, depend on how we divide it. For our last case, which is maximum subarray, A and B are both 2, which indicates that we divide the array into 2 halves and we apply recursion on both halves. Then the Fn, which is the time complexity we use in the combined step. Let us see an example. For our maximum subarray problem, let T and T denote the running time for an array of length n, and what we did is that we run the same algorithm on we call ourselves like doing recursion on the left half, and then we call recursion on the right half, and both can be denoted by Tn divided by 2. And when n is equal to 1, it's a constant time. Otherwise, we divide the question by 2 and call it twice. Plus this On as the time complexity we use in the combined step. And then we can prove by our memorization merge sort, the time complexity would be n log n. Let's conclude today's workshop. Just kidding. So we're gonna use the master theorem, and in this case, A equal to 2 and B equal to 2. Then we found that case 2 applied, and we also know that Fn equal to On. Then we just plug in the number and we get this theta, big theta, and log n, and which is our also align with our memorization of merge sorts complexity. And let's do a slightly harder question, but it also uses the similar sort of idea that we apply in the last problem. And this concludes the first part of this workshop. I'll be recording the second part in a short period of time. And thank you for watching. Thank you.